Hello, welcome to Advanced Composites. Today is the second day of the 11th week of this course. Yesterday we were developing equations of equilibrium for a composite plate when the plate is in the deformed position, and in yesterday's discussion we found that even in the deformed position the equations of equilibrium for specifically for force equilibrium, they do not change, corresponding to force equilibrium in x direction and force equilibrium in the y direction. The next thing we are going to look at is force equilibrium in the z direction. So, this is the third equilibrium equation, which is sum of all the forces is equal to 0 when the body is in equilibrium, that is when the body is in the deformed state. So, I will make this picture again. So, once again this is an over amplified view of the scheme of things. This is my x axis, this is my y axis, and now what I am interested in finding out is sum of forces in the x direction, in the z direction. So, what are the forces in the z direction? One is Q, which is per unit area. Then there are out of plane shear resultants, which we had expressed as Qx and Qy. Okay. So, this is Qx plus del Qx over del x times del x, and here you have Qx. Okay. Likewise, you have also Qy plus del Qy over del y times del y, and likewise on the other face we have Qy moving up. Now, there is something extra on top of that, because there is curvature. My nx is, let us say, in this direction, and it will also have a vertical component. Okay, it will also have a vertical component. So, this nx is nx plus del nx over del x times del x, and it is at an angle theta plus delta theta. So, what is this angle? It is theta plus delta theta over del x times del x, and theta we have defined it as del w over del x. Okay. So, likewise here this is theta, and here I have nx. So, if I have to add up all the forces in the z direction and I have to equate them to 0, then what are the forces? So, these are the forces, but then I also have forces related to nxy and ny likewise also. So, here we are just going to illustrate the vertical components associated with nx, but we will also have vertical components associated with nxy, nyx and ny. So, the only thing we are going to calculate here is the vertical component associated with nx, and all other components can be calculated in the similar way which we have discussed, which we are discussing. So, here the plate, if it is bending in the x direction, we call it theta x, and if it is bending in the y direction, we call it theta y. So, this is theta x. Okay. So, So here we have extra terms due to nx, nxy, nyx and ny, and we will only compute the extra term due to nxy, nx, okay, and then we will just write down the result for the overall thing. So extra term due to nx, what is the extra term? So this nx will have a vertical component, so it will be, what is the force, total force? Nx into delta y, nx, it will be delta y. So it will be nx plus del nx over del x times del x. So this is force per unit length times delta y, that is the total force, times the sine of this angle, sine of this angle. Now this angle, sine of this angle is theta x. So this, so what is theta x plus del theta x over del x times del x, delta x? This is, if I substitute theta x by dw dx, so I get delta plus second derivative of w, and these are mid plane displacements, del x square times delta x. Okay. So I have to multiply this by sine of okay. So this is the force in the, on the positive plane, and in the negative plane it is acting on the negative direction. So it is nx times delta y times sine of delta w over delta x. Okay. Now again I said that these angles are very small, and if the angle is 0, then the sign of this entire expression in the thing will be 0. But if the angle is very small, and if I compare a small number to 0, I cannot ignore it, because I am comparing it to 0. Okay. So in that, because of that reason, earlier when we were taking cosine, I was taking cosine of a number very close to 1 and a cosine of 0, they are same. But here those differences are appreciable when I compare the sine of this angle to sine of 0. So if this angle is very small, then the sine of this angle is same as the angle. Okay. So I get nx plus del nx over del x times del x del y, and then I have del plus del x del 2 w naught over del x square minus nx delta y del w naught over del x. Okay. So I get, if I simplify this, what do I get? The contribution from nx, so this term cancels out when this gets multiplied by this term. So the terms which I have left with are 3 terms. So what are those 3 terms? So the first term is, if I multiply del nx over x, so what I get is del nx over del x times delta x delta y times del w over del x, this is 1, plus nx times delta x square delta y this thing plus I get del, and then I have to multiply del nx over del x times delta x square delta y times delta w over second derivative with respect to same. So,
Why there should be del x square in the second term? Del x.
so this is there. Okay. So, these are the residual terms. So, these are additional terms. Okay. So, these are the additional terms. Likewise, we will also get extra terms due to nxy, nyx and ny. Okay. So, likewise we will get extra terms also due to nxy, nyx and ny. So, we add, so what we have to do is we have to compute all these terms using this methodology and add up all those terms. For the original equation for the z direction was, so for undeformed geometry, what was the original equilibrium equation? So, if I did fz is equal to 0, it gave me del qx over del x plus del qy over del y plus q xy equals 0. This is what it gave me. Now, for deformed geometry, after including extra terms, so what do we get? But before we include extra terms, I wanted to make one more comment. See, here I have a multiple of delta x, delta y. Here I again have a multiple of delta x and delta y. But here I have a multiple of delta x square times delta y. So, if I make my delta x and delta y extremely 0, this term will very rapidly vanish to 0. So, I can drop this term and it will not make any difference to my results, because if I make everything 100 times less, this will become less by in even faster pace. Okay. So, this I am going to drop because it is a higher order term. So, I am going to drop. So, from each of these nx, nxy, nyx and ny, I get 2 extra terms. And if I add all those terms and include them in this equation, my overall new equilibrium equation for the deformed geometry we get. So, I am just going to write down the equation. So, it is del qx over del x plus del qy over del y plus. So, the new equations which I get are nx del 2 w naught over del x square plus nxy twice del 2 w naught over del x del y plus ny del 2 w naught over del y square plus del x, and in the bracket we have del nx over del x plus del nxy over del y plus del w over del y, del n x y over del x plus del n y over del y plus q x y equals 0. Okay. Now, this term in the bracket, this is 0. Why is this 0? Because of the first equilibrium equation. What is our first equilibrium equation? We have developed it and we have seen it several times. So, this is the first equilibrium equation. Okay. So, this is 0 because of the first equilibrium equation, which is sum of forces in the x direction is 0, and the corresponding equation is actually this thing. So, it has to be 0. Similarly, this term should be equal to 0 because of second equilibrium equation, which is sum of forces in the y direction is equal to 0. Okay. So, my final equation for the third direction is this guy. Okay. So, this is my modified equilibrium equation for the z direction if I consider the deformed shape of the system. Okay. Then these terms involving nx also appear in the third equilibrium equation. Now, we can do this analysis further, and what we will do is we will complete the remaining 3 equations in tomorrow's class, and then we will actually start solving some of these equations and see how using these equations we can predict buckling loads for different types of plates. So, this is what I wanted to discuss today, and I look forward to seeing you in tomorrow's class as well. Thank you.